for the worst case efficiency, so let us use a principle we learned before to get some idea. Balancing principle. Based on that, we know when we arrange our data, in order to get the best case efficiency, we should choose the most balanced arrangement. The opposite way also true. If we want to get worst case efficiency, we may need to consider the most unbalanced arrangement. All right, so now we go that direction, the opposite direction. Try to find the most unbalanced data arrangement. All right, so look at this. This is the most unbalanced because the L region empty, nothing, right? Yeah, okay, yeah. Another case similar, this time L region S region empty. Yeah. So for the both cases, we need n-1 comparisons. All right. The first one, let's refer it to S case. Second one, L case. Later we will use these two names to refer to these two cases. If we still want to compare these two cases, which one is slightly better, although they have the same number of comparisons, we want to see can we find one that is slightly better than the other? Okay, yeah, or equally worse. Yeah. I think we can consider the swap operation. These two cases are different regarding the swap operations. For the first one, the swap, there is no swap. Okay. But for the second one, the second one, we need to put the pivot in place. So that's why we need one swap to do that. Okay? So that means the second one is slightly slower than the first one. Okay? Yeah. Due to this special operation. All right. Now let's derive recurrence equation for the worst case. Here we only consider comparisons. Yeah. The swap operation much more complicated. So let us delay the discussion a little bit. Yeah. All right. So here the size reduction, the problem size reduction after one partition, the size reduction only by one size smaller than the previous one. Yeah. That's very slow. Okay. All right. But we can get a recurrence relation in this way. So let us use T of n as the running time complexity function, or the number of comparisons represent. Yeah. Then T of 1 equals, when we do the partition, we need to pay n-1 comparisons. After that, we reduce the problem to n-1 size, so we need to call this recursive function another time. Okay. So in this way, we can find the original function, T of n. Yeah. The answer is this. I hope you can see it easily. Yeah. Here, let me show you how to do it. Okay. Let's do the second time, n-2. Then we need to have this n-2 term plus the previous n-1 term. Okay. So let's keep doing this all the way to the last one when we reach the base case, t of 1. This time plus 1. Why? Because they should have the same size. Observing the previous cases, they have the same size. So that's why we get this. All right. The last one, n minus 1. Because t of 1 equals 0. Okay. No comparison if there is one element. So then we get an answer. Okay. And finally, it is big theta of n squared. So you can see the worst case is pretty slow. Yeah. But we don't worry about it because in our part 1, B.1, we know the probability that this could happen very low. Okay? Yeah. Next, we want to look at inputs. What kind of inputs would cause the worst case? Yeah. S case all the way. So let's consider this situation for data in increasing order. In that case, we know the pivot is the largest. So we get a S case. But the next time when we use the last element as the pivot, also largest. Okay? Always we use the largest element as the pivot. So that's why the S case all the way. Okay? Similarly, let's look at another similar situation, array in decreasing order. In that situation, this time we have L region with respect to this pivot element. The question is, do we have that L case all the way? The answer is not. Why? Because in this case, we need to do a swap. Okay? After the swap, the new last element will be largest. Okay? If it is the largest, the next time we will have an S case. So you can see the first time L case, the second time S case. Okay? So you can see actually what we have, SL alternating case. Okay? To see that, let me use a simple example to see that. Okay? This example, array in descending order. Okay? The first time, the smallest element as the pivot. So we have an L case. Then after one swap, so we do swap. This time, the largest element becomes the pivot. So we have an S case. Then the smallest element as the pivot, we have an L case. Right? Yeah. Next time, largest element as the pivot, we have an S case. The smallest element, pivot, L case. Okay? The largest element, the pivot, S case. So you can see alternating. Okay? Yeah. So that's what we usually have for the worst case. Okay? Yeah. All right. Next, let us look at the best case analysis.